neurons sitting inside each layer need not be the same. I represented something like there are K1 neurons in the first layer, K2 in the second layer, and Lth layer you have Kl neurons. So that will generalize the formulae, the mathematical expression. Before that, let's simply try to build this one. Yeah. So anyone tell me what's happening here?
Sir, I have
Yeah.
tried, sir, but sir, I did not get how to reduce the sir like numbers. Sir, like for every time we have to reduce by one, sir. Like it's for only four. If we go for RN, then
Mm.
I I have stuck that point, sir. How to reduce by one? Sir.
Mhm. So first analyze what's happening for every time when you choose a neural network of this kind. So think of only you are passing the information from here very first, and for every this is just the raw information, that is there are singular points. Let's say each coordinate is x1, x2, x3, x4. Then this is a element inside x1, x2, x3, x4 is belongs to R4. You are passing it, and there are kind of weights are sitting here. The weights. So these weights, how many weights are sitting in between the input layer and the first hidden layer? That is again the number of going in and the number of hidden sitting. So all possible combinations, that would be 3 times 4. So there are so you can name them each one as like wij, where wij you can name it as like the weight or the weight connection, I can say weight connection from uh, weight connection from I to j. That means like if this is if this is the ith node, and let's say this is a jth node, then the node associated sitting here, this one is called as a the weight sitting inside this edge is called the wij. And if this is this one, this is another wij. Let's say this is 1 2 3 4, and this is 1 2 3, the edge. This is w33, this is a w43, this is a w42, and so on and so forth. So if we give them connection, let's compute one particular piece. Let's say let's compute this piece. This, what is this? This is the neuron, which has a computational unit, and it gathers the information from every other node, from various weights associated to it. That is like you can say uh, w the w I to 2. I is varying every time. So if this j is equal to 2, then whatever gathering for all the i's to this node. So there are such gathering. Then what you are doing with that one? So you are multiplying with the inputs with x1, x2, x3. So wi2, you keep it as a vector. That would be a wi2 transpose. wi2 transpose. Wit is the four components, and since I is varying from 1 to 4, all the inputs are gathered there. So there are four components, and you are multiplying with these four components. That would takes place wi2 transpose x. And of course, we are okay. Let us write that another component is there. That is what we say the bias component. That is also I will add up with a little different color there. Um, okay, this is also going there with another component that is like b1, b2, b3, whatever we are passing it. So wi2 x plus let's say that is b2. So plus B2. So what is coming into that particular node is this component, this amount. So that is this one, the computation. This is the real number. This we are naming it as affine function. This some you can take it as affine function. Let's say A2. The 2 is referring because of j equal to 2 we are considering. For this one, you can say it is a A1. For this one, you can say A2. For this one, you can say A3. And instead of that one, I can say above there, I will keep it as a 1. So what it is representing the superscript indicating for the first layer, and 2 is indicating the subscript is indicating the number, the neuron number. So that means like this I can call it as A11, this is A12, this is A13. That is affine function. Every affine function taking inputs from the same x1, x2, x3, the weights associated connected to it in this format. So these are the two things. That is the first computation. What's happening there? If you write up whatever I explained that one, what is this one? That is a kind of simply if I remove this transpose and everything, I think and this okay, that individual components we are gathering it, that we can call it as like uh, the single hidden layer. If you have if it is there, then what is coming out of that one is this one, and for each one, and there is a continuous function sitting in there. That is I can call it as a g of uh, g of what do you say, this each one a, the first layer I could say that a, the affine functions are sitting inside the a1 I. This I is varying for 1 to 3, right? AI of x. This is what you are doing it. So AI of 1 is this component actually. This one is the structure of this AI. The one is representing for the first hidden layer. Okay. Now this is what each one is coming out of it. The outcome of this one, the outcome of this one, the outcome of this one. Okay, these are all outcomes after applying the G activation function too. So now this one is, now you have to think of this I is varying from um, for everything. Like if you look at, I think I have already highlighted what it is going there. Outcome of this one is this place. Now you have to compute just for one. Then you can think of what it is. This one. This is computing of all these components for this one, this one, this one, or you are summing up with some weight. That is how you calculated if you look at, yeah, this one. If you look at simply, not this vectorized form, single, I will show. Yeah, this one. The earlier, if you look at it, this one is the outcome of a single neuron, and when you are combining with again a special weights with betas, and you are summing up with this one. Whenever you are combining them, linear combination. That's what I could say. So now this is a linear combination of all these outcomes with some again there are weights. So that we have to do. That is some. Okay, I will need to keep it as some weights before it. Uh, let's say that is going out with this particular hmm, outcome. This one what we are targeting here. Then you how many combinations are there? There are three combinations are going there. So that I need to look for what are those three. I is varying. The I is varying with 1 to 3 for uh, every neuron in the first layer with the associated weights. Again, there are weights here sitting inside this one, these weights. And those weights, okay, I will rename little bit weight naming convention. Earlier, I have mentioned here Wij. Instead of Wij, I will keep it here superscript 1. The 1 is representing for that, like that is for the weights associated in the first layer. Now, the weights associated are the second layer. So W1 Ij I will write up here, W2 Ij, the weights notation. The superscript is always I am, you can think of like it is a layer dependent, so that you don't need of confusion with different symbols. So now this one is AI, this one, so that I can keep those, what weights comes here. Can you tell me? Now you can guess it. You can fill it up. One or two? Wij one or Wij two?
WIJ2, sir.
Yeah. Here Wij two. Now you may ask me question like again, what is here I and J? Here again there is a problem here. This I we haven't defined that. Like I is okay. The I is that like the incoming from like from here to here. It is going there, and this I is are the affine functions there. And now we have again another affine functions here. Hmm. These affine functions I can name them as A1, 2. This affine function is like A. Sorry, this is like A2, 2. So now what's happening here? So now the weights associated here is a W2Ij, but here the, they are going it for one particular one, that is A1 and A2. I take them as a J's. So that first one, the I's are fine, WI, and the second one where it is going, that is what I have defined Wij notations here. Like you look at here Wij dash, it is a weight connected from I to J. Now I is acting as this one and J is acting as this one. So that is the J comes here, that I need to again express further what that J means. So now that we will see that I am just shifting aside a little bit. Uh, so now this J is at to elaborate what is that J. That J means vertically it is varying for this one and this one. For this one, these things are there like for J2, and for this one J is 1. So 1 we have finished this one. this one. Now j is varying. If j equal to 1, then this is the component is this one, and if j equal to 2, then that is the component it is computing this one, the weights associated with this one. Got it, right? Little notationally tricky, but you can uh, understand very well because of the the weights, the affine functions. We have to symbolize very properly, not to um, not to get confused with what you are using, what index which you are using for which one. Now, this is just a linear combination. After coming out of the linear combination, then we need another, again there is a activation function also, that is g sitting there. The g is again on top of it, that g comes here. The g is sitting there, and now okay, let me take this one. This is becoming bigger expression, so take it into the next phase so that I can cleanly write up. Yeah, now the G is coming out of it. The G, whatever apply after applying the activation function, it is coming out of the G, and here it is the activation function with the affine, and here it is again activation function with the affine, and again the same process is repeating another one more time. That is the same whatever we do it for here, and the same it is repeating there. So for that, what you are doing here, for that now we need to just again repeat the same. How many? So again, there are three here, and again there are two such. There are two such weights are associated for those summation. Again, what summation? What you have to do? The j comes here. J equal to 1 to 2 for two neurons. This one and this one. And what associated here? The weights are sitting here. You can say the weights. The outer layer weights always I maintains the betas instead of ijs, because those are coming out anyway. Beta ijs. The So you can think of the beta. Here we don't need of use two notations here, since we are almost comes out of it. So I don't have any kind of like to use them further to continue with another one more, so that I will keep a single representation beta j instead of beta ij. So this one is for beta 1, this one is for beta 2. So I and j is varying for 1 to 2. The same j, if you look at here, the same whatever we left here, that is same j connects there. So that this is a whole expression of what we are thinking of the complete linear combination. But still one more thing need to be attached. What I can attach is that I did not take another one more care here, that is also need to be taken care. There may be bias in the each hidden layer as well. If there is another one more bias here, and this goes here, and if there is another one more bias here, that is also goes there. So that need to be add up here. How I am going to add up here? That one. So if I complete with that bias, so that for this for this one the bias is adding for each affine function, so that means that I need to attach that into this internal summation, plus plus what bias name I could keep here. So this bias I can take it as a B1, this bias I can take it as a B2, this bias I can take it as a B3. B1 is the BIOS going for the first layer, B2 is going for the second layer, B3 is going for the outer layer. I can say you can decide what BIOS uh, names you can give it. So now that is like there are two BIOS always. Like it is not just the B2 is a vector actually. It is going this one as well as this one. That is B21, B22, and this one is B11, B12, B13, and this one is just a B3. There is only one edge is there. So now, for taking that indices into the consideration, and the second layer, that is B2, how many? There are two such. B2, what index will come? B2I will come or B2J will come? What will come there? Hello? The subscript index, what will come here? Look at it, where we are applying this one. This is a linear combination of the three components, and on top of it, we are applying a complete G. We have to activate a G here with this one and activate a G here with this one. There are only with the two. So 2 means that is only with the J. Then again there is this one here. Again there is a B3. You can take it as a scalar, that B3 that is sitting here with this one. Plus you can say just B3. Now we have completed everything. This is the expression. So now you think of it how to generalize. So there is a B1 is sitting inside this affine function. Actually, we have written this form very compact way. So that like okay, I think I should write B1 subscript here. Yeah. Now this is the functional expression for this diagram. So you think of like to generalize the complete structure. How do you write up this? So that, and again you need to bring up all the things into the collection. So far whatever classes we have seen, that is sigma. Uh, I forgot the notations what I use it to. Okay, sigma n of g, sigma n of g. Okay, sigma n of g and sigma uh, n comma m of g. The classes. This is a single layer. These two are single layer with R into R. This is R into RM. And what else we have seen? The multi-layer, we can say, that is sigma. You can name it as sigma n of g with did I mention anywhere any particular rotation? Okay, I just mentioned here equal to k1 k2 kl. So the sequence, so that you can write up this L equal to the ordered layers L1, L2, and so on. L LK. There are K layers, or otherwise I can say that like the number of layers like L equal to K1, K2, and so on KL. So that K1 neurons in the first layer, K2 neurons in the second layer, KL KL layers, sorry, KL neurons in the Lth layer. That is what we have just seen. Now your task is to write up the expression for the class of functions for an Rn to Rm with L equal to K1, K2, and so on KL of G. There are four such classes we can say. As of now, so far we have discussed these things, the four classes, neural network classes, and today I will go with another one more class. This is a quite different class of neural networks. Yeah. So this, okay, I first of all I'm thinking like what to express, like if a diagram or a mathematical expression. Let me go with the diagram. That would be better. Um, so let's say I have something. Okay, I will go with not a in general one. Let me go with R to R. I will say R to R. So I have an R2. It taking two inputs, and now I have uh, uh, something I need to do very interesting way. Need to express a diagram of two components, whereas wait a minute, I'm just thinking to simplify the diagram, not to complicate. Okay, I will write up a diagrammatic way, but I will combine the diagram little bit simpler version. But let me take this way the components. Then let me draw something randomly what comes in my brain. Then we'll simplify on the go. So I have some kind of uh, single. Okay, let me write up first for single layer. If I have G A1, G A2, all these things, like say this is this is GA1. Let's say this is GA2. Let me say another one more neuron, GA3. The three hidden layers. Oh, sorry, one hidden layer with three neurons. Um, Now, uh, in general, you know that like this is x1, this is x2. We stop here and we do this all connections and combinations, and that's the usual thing. But now I don't want to do that usual one. That's I just wanted to go with something different way. Instead of just not just the GA1, GA2, I need to repeat this process for several times. The components I need to associate for several times. That means like it's a little complex situation here to define the process. Um, so the product of this one is okay. I will keep another one more at the end as a output. From this, I will do this one. Suppose, suppose uh, this GA1 and this GA1 repeated for several times. Give me a minute. I need to establish very perfectly. Okay. I am keeping here some intermediary setting. And let's say this is for this one, and um, no, no, no. Okay, and let me keep some two such intermediary settings. Okay, I'll just keep some kind of temporary things here. These components receives information from uh, let's say from this one to this one, and this one to this one, and another one more. I just wanted to it's insufficient to describe this way. Another one more. I wanted to keep it here to make it perfection. Maybe this one to here, this one to here, then this one to here. Just use this one to here, this one to here. Okay, please hold for some time because I may modify this one once my thought process gets very clear distinction with the idea what I'm thinking. So yeah, these are fine. Like uh, from here to here, from here to here. This is fine. This is usual way of representing. and this one to this one. Now I will explain these pink color ones. What actually I was thinking to give the information like let me write up mathematics so that from the mathematical expression I may think of what I am thinking. Uh, G A J K not J K G A I J. Okay. Slight modifications in this, like I will. Since I am coupled with G, actually, it is troubling me. So I just wanted to decouple the GS so that maybe the diagram would be easy. So what I do, I will just separate it out completely. The this affine functions with the G, so I can do much simplest way. I feel like rather than G and A together. So let's say I have something like GA11, GA12, GA21, GA22, A21, A22, something. I have 11, 12, 21, 22. I just hold for those affine functions, four different affine functions. Now, uh, I'm acting the G on top of this one. For this one G, yeah, the same G, of course. I will act as a G on top of it, and another G acting on this G on top of it, and this one acting G on top of it, and the G is acting on top of it separately. Now, what I do is there is uh, I will keep here some composition, a different colored one. This one with this one, this one with this one, this one with this one, this one with this one. This I am producting it. I am just multiplying the outcomes with of course, with some weights associated to it. I don't think I don't need a weight here. We'll say all the flow from here to here, here to here is same. All the flow from here to here, there are no weights are here. These are all unweighted. These are not actually connections. This I could say that like these are all um, and the computational continuity. There is no, uh, I don't think there would be weights. We can keep it there as the weights are already sitting here in this. Okay, computational flow, I could say, and now I could say this is a product. This is a product of these two. Then after these products, then finally the output we have again weights here. I will keep these with a different color, so where we are not having any weight in this, and this one is final f of x. It's some beta 1, beta 2 weights. Yeah. So now this one, this combination, the whatever I am just written here, this is a kind of like the affine function which we are taking all these things. This one is also we are taking it. Yeah. So now the new thing is kind of like uh, earlier we have GA1, GA2, all the things were collected together, but we are not doing it. We are GA1. This GA1, this GA2 are comes in this channel, and this GA group is comes into the separate channel. So this pi is doing a product. Okay, so this is yeah, I think, yeah, now it comes to a perfect clarity while writing up in by splitting up the actions G with affine functions. So now this is a neural network again. Only the difference is that we are not taking everything all together. The only difference with earlier sigma G, simple R into R, sigma G is we don't have this thing, and we combine this one to here the final answers. Now we are not doing that. We separated out some of the affine functions with some group, some of the affine functions with another group, and we are making it as separately, and we are dividing into multiple groups and producting them. So then it is channelizing into a different way. Instead of keeping all the things together, we are grouping them and producting them. Okay, this is the affine function grouping instead of just simply the earlier ones. So this is a final kind of like the main distinction is here. This one we grouped them instead of taking everything together. Okay, how we grouped it? We grouped it into these two in one group on producting, and these two into one group on producting. We are just producting. There is no linear combination here. This is a product of this outcome and a product of this outcome. The product of this outcome and this product. This pi is actually the symbol of product. It is multiplying the outcomes from here. And then we are doing this beta ones and beta twos. Okay. So now, if we express this one, so that means what we do, we are all actually that has the right this mathematical expression how it goes. So this f of x,
Sir,
what we are do,
could
yeah,
we write sigma I equal to 1 to 2
okay,
for
you
this
are
one, sir?
saying the final expression.
Yes, sir.
Okay, sigma I equal to 1 to 2, yeah,
Beta I
beta I.
pi of
Okay,
j
the
equal
pi,
to 1 to 2 pi
pi is the product.
multiplication.
Yeah,
Yes, sir.
multiplication pi.
J equal to 1 to 2.
I don't. Okay, but okay. For this diagram, j equal to 1 to 2.
G of a I j x.
G of a
A.
I j. Yeah, a I j of x. Yeah,
Yes, sir. I think for this diagram it will work only.
yeah. G of a I j of x. Yeah, this is fine. So, yeah, that is the one you can say, like here, like the betas are belongs to real number and everything is same. Yeah, this is the functional representation. That's the same. Like when you think of the product is a kind of like we channelized for every two groups. We have channelized this one and this one with this one, this one with this one with this one. So AIJs are the symbols, like that is why we have not just the simply single index. We have multi-index. We have chosen the multi-index is actually playing the role here to group which ones are going to which group. Like this one, the one with the first index going into the one group, and the second index going into the first index as a two is going to the another group. So you can think of like this I is actually seeing the number of groups we are divided. So in general, if we write up this one, f is a function from R and to R. If multiple groups, I don't want to just keep it for only two and two. Yeah, I may have first three into the one group and last two into the another group. So like the first one is going for only one group. It is not doing it. The last three is another one group. Like this by these three are coming into this group. So the in such case, the groups can be multiple ways we can express. So f of x we can write up as summation I equal to 1 to let's say the outcomes, the number of groups comes here. We don't know that. I can take it up like let's say um, there are what which symbol I can use, the k. I can use it k. There are k groups, and for everything there is a beta for everyone. And now product is kind of like varying from uh, product is varying from j equal to 1 to, for every
I.
one we have different groups. So for j equal to 1 to, I can say that the groups, um, I can say that depends upon the I. Each group
Yes, sir.
is
Like
depends upon. Yeah.
we can say j
Mm,
equal to 1 to I, sir.
no, not 1 to I. J equal to 1 to GI, the group GI. So GI maybe varies for each one. The GI is the number which is associating with each group. So like it need not be exactly the three ones. It may be a two ones. It may be a first group. It may have three, and second group may have only one. So in that case, one G1 is three and G2 is one. Here in this case, G1 equal to G2 equal to 2 only. That is the two things goes there, two things goes here. That is GI, the group, I could say. The GI, it rest everything same. G of A I J of X. Okay, this is actually the bigger class. This is the bigger class. That means like if I write up the class collection of all functions from the neural networks from Rn to R, such that f of x is following summation I equal to 1 to k, um, beta I pi j equal to 1 to gi, g of aij of x, so where if you write up like where the beta i's are belongs to real numbers and aij's are belongs to we have some symbol I forgot, like I guess like I used this one, the affine functions from Rn to R, and g is a fixed thing, of course. I don't need to mention that. What else? What is varying here other than this? Yeah, gi's are belongs to natural numbers, and what indices k is also varying. K, how many groups we can define, that is k equal to 1, 2, and so on, the number of neurons, the connect linear combinations, that's what we can say. So this is we can name it as a bigger class, that is sigma pi nets. This is actually the bigger, much bigger class, as this is sigma pi nets of g. This is sigma pi of g. Okay, I will keep it as a sigma pi n. That is n is for n to r. N dimensional to one dimensional, like sigma pi. Now, if you think of like our original beginning, the sigma n of g is a subset of this one. Could you look at it? How it can be a subset?
Sir, here we can say our group layer, like our product group,
Mm,
uh, can show the one hidden layer also, sir. Like how many groups we form, like k
mm,
groups we form. So then at the starting, sir, how many hidden layers in the sigma nj. So
mm,
we
mm.
can relate that our
Yeah,
because
simply that is like gi equal to 1 for all I.
yes, sir.
If you gi equal to 1 means you are not doing any production, you are not forming any groups. If this term is excluded, look at the expression, right? If you
Yes, sir.
just
Yes.
remove, yeah, if there is no product, it means only one term is there. You are not doing any product. That means you are literally removing this one. The simply the expression is sigma n of g. So it is a sigma ng. Okay, this is a huge class. And this is our special class. What so far we discussed is special class. That is a classical ANNs, artificial neural networks, with single layer or multi layers. And this is a sigma pi nets, which is a bigger class of neural networks. So this is also again dense in all the properties for so far whatever we discussed. All things holds here actually, and so that those things holds in this. Actually, the classical theorems proves on this one, so that it covers a larger class. So then it applies to a smaller class as well. That is a analytical theory of a different thing. Now, like sigma pi nets, sigma nets, sigma pi nets, all these things. So far, we have defined these classes. So now I have So far, whatever we are discussing, there is no computer, there is no kind of like algorithms. So far, like it is a theory of neural networks, theory of I don't call it as a neural sigma nets. So far, from there we extracted a lot of features and saying computational names called as artificial neural networks or whatever can name them. But these are all mathematical class of functions sitting inside higher dimension classes like continuous or Borel measurable functions, class of functions. Now they are doing good. That's what yeah, we convince with theory. So what? So where we are going? Like from? Let me recap the things what so far and where we are heading and how will we continue from here. And let me briefly give a direction so you will be knowing what we are discussing. So the theory, mathematical theory, mostly analysis. I can say analysis, and then I convert slowly this analysis into mm, methods, methods to computer, because this analysis doesn't have anything to do with computers. Analysis just for to prove them. They are mathematically satisfying, and the rules are holds mathematical rules. So now we need to bring that theory into forms of like uh, methods to solve or problem solving. You can say methods, develop methods, I could say develop methods to make use of solving real problems. So such tools like using those methodologies involves linear algebra heavily, linear algebra and optimization, mostly these two, and there are other things as well, higher dimensional calculus, those things we can see. I can say higher dimensional calculus, chain rule, all those things comes there. So these while developing this one, we have to compromise certain things. So uh, before touching these things, I will bring one thing like linear algebra into the picture. How do we convert these classical functions, these expressions into matrix language? That is what linear algebra comes into the play. Now, next job, immediate job is so far. I think slowly I will go away from the theory and bring those theoretical ideas into the um, models are developing mathematical, concrete, computationally possible um, algorithms so that we can use them, code them, or we can apply whatever we want it to be. So, so for that, the linear algebra is doing the task that is called matrix algebra, you could say. So how do we these continuous functions bring it down to the matrix language? That's what the next step I will go ahead. That I will touch bit later, not today. And that is a simple thing. It won't take much time. Uh, so then after converting that into the matrix language, from the matrix language, how can we convert? How can we use those rules, matrix rules, and use the higher dimensional calculus to approximate functions from the data. That for that we need to rigorously look at all these things. Okay. That's what my next goal. But today I will not teach those things. I will go little off from the neural network. And of course, I am not going completely off from the neural network. And slightly, I just wanted to touch our basics mathematics, where and how we can uh, look at generalizing the functions or approximating the functions using basic principles of mathematics. And why neural networks are so special, why not others? That's what my target. Like, why neural networks are coming into the place of kind of current technologies, but not the something like Fourier series is there, Taylor series is there, power series is there. You know them all these, right? So why those class of functions are not doing this job? Are they doing, or are they failing to do something? Or what are the drawbacks with them? Why this class of functions only doing this job very good way, or the predictions or whatever? So for that, I will pose some abstract questions to you. You work it out, like think with me and discuss with me, and maybe even most of the things I haven't thought processed, but I will on the go with you in the discussion. I maybe get a better clarity, or maybe give some intuitions behind them, so that we will think on them. Yeah. Um, like, I will put a start with, like, Taylor series. Let's start with a simplest case, the Taylor series. Let's start talk with only functions from R to R, approximating functions from R to R. F of x, let's say. I am not mentioning anything, any function like x square or e for x or log x, whatever. F of x. Um, if is, let's say, um, is continuous,
To explain.
I'm mentioning zero. Means I have not mentioned anything like x. If it is mentioned like x minus a, that is a point around a. But I'm just mentioning p of, yeah, around zero.
Then I guess so f of 0 plus f dash of 0 into x plus f
F
double
of
dash
zero,
of 0
f of zero plus f dash of zero
into x
into x plus,
plus f double dash of 0 into x square by 2 factorial.
okay, 2
And
factorial plus, and so on.
f yes sir.
Okay, that's cool. Now, if I collect all those Taylor series functions, t of x in general, if I write up like a zero plus a one x plus a two x square by 2 factorial plus a three x cube by 3 factorial plus, and so on. Okay. So now only the rest everything same. The f of zero, f double dash f zero, f three double dash, f triple dash, all those things I have kept in terms of a1, a2, a3. If I know a1, a2, a3, then it is approximating some function, right?
Sir,
Okay. If I replace a0, a1, a2, a3, and so on, ai's with some numbers, definitely does it approximating some function?
yes sir.
And like, if I collect all those class of functions, like all those t of x of the above form, such that like, let me write up t of x is in terms of summation I equal to 0 to infinity ai x rise I by I factorial. That's fine, right? such
Yes, sir.
that all A's belongs to real number. Is a class of functions. Does now this class is exhausting all the functions of continuous or not? That is our question now. Think of it. I will come back in 2 minutes. Think. What to think? As this class, whatever I written all the Taylor series, you usually do with like you taken a function and you do this and you come up with some approximation like this and you are satisfied. Now I am doing in a reverse way. I'm taking all possible cases of this one with modifying all these coefficients of a Taylor. And now I'm asking that does it and taking account of all the continuous ones.
No, sir. I think from
Yeah.
reverse way we cannot get always a continuous function, sir.
Okay. So why?
Why, sir? Because sir, for like if we fix any number, sir, like a1 a0 is a real number, sir. From that real number, how we can say ki that point should be always a any differentiability value, like if there is something point value.
But if you think of this as a constant is a continuous. It's a polylinear. It is a continuous. It is a quadratic. Quadratic is a continuous. Cubic is a polynomial, right? Okay. So infinitely many polynomials. Taylor polynomials. We say all polynomials are continuous. Take some time, 2 minutes or 5 minutes, and strongly suggest. If you remember, maybe real analysis. I did not discuss that part actually. Something called the Stone-Weierstrass theorem, Weierstrass approximation theorem. Have you come across any time in your life? Hello.
Yes, sir. Yes, sir. I guess in real analysis, sir.
Yeah, I think I did not discuss that Weierstrass approximation. You just take a Weierstrass approximation statement and read it and think my question and come to some conclusion and tell me what I am asking on my question. Read the Weierstrass approximation theorem first before answering my question. Okay, I will be back in 2 minutes. Hold your answer with you. So yeah, you can tell me now. So now think of like functions from the same perception. Like I am keep continuing the discussion further. Like instead of t of x, let's say this class of functions. Am I audible? First of all, can you hear me?
Yes, sir.
Okay,
Yes,
fine.
sir.
Yeah, like let me uh, some kind of notation. I'm just keeping it script T, the Taylor's functions. Uh, Now mm, the sigma n and this script and the Taylor things. I want to see like what is are they okay to go with, especially function from R to R. So which one would be much better, like the sigma nets or Taylor's? And what are the advantages of one with other, disadvantages of one with other? This you know it, Taylor series. I don't need to describe their features and all. Enough exercises. But this is the neural nets. We are not looking for all the higher dimension. Let's focus on for only um, this one, R to R case, real number case at least. Then we can think of what goes in the higher dimensions later. So I can keep here n equal to 1.
And for linear function approximation, I think Taylor would be more good as compared to neural network, because in neural network we have to modify, I think, more than two constant, but in Taylor we have only two constants. So, like for if
For
we
linear,
use,
neural network only two constants. You don't need of because of even you have multiple. You can have lot of other things. The linear combination of okay. Let me this one. You have a neural network. If you don't have the outcome is, so this one is a1, a2 affine function, a3, and you have k affine functions. No matter how many affine functions you choose, the hidden layers, and if our activation function is g equal to 1, not g equal to 1, g equal to identity, then again all these things reduces to single hidden layer, single neuron, nothing else. This is just simply some a. So again, affine function contains only uh, two things. So for the linear case at least. You understand what I'm saying?
yes sir, yes sir.
Yeah. Don't look for answers from me. This is a free-minded, open thinking. Forget about your course. Forget about everything. It is not a lecture. You just think for yourself to understand the mathematics in core way. Experiment yourself. Like what's happening? What is happening in the world of functions? At least in the real functions. It's an open discussion. So you should know what is like when you have something f of x equal to some sin x or cos x or x square log x. I don't take log because it has a lot of singularities. Let's continue take up uh, everywhere continuity functions. E for x, such functions. Let's say a lot of
There is
functions.
for linear functions, sir, like there is one issue, sir, differentiation, sir. If we apply Taylor, sir, we cannot beyond that, like one differentiable, like f dash only exist. After that, f double dash not.
Then it is
Then
so perfect. Like if you don't have double dash, that will become zero. Means you come across with exact solution. Linear functions are exactly we can determine. That is, you are predicting it. You are producing it here. Linear functions are this form only, ax plus b. You are getting it ax plus b only. Why are you expecting this one in the linear? If it is coming, then it is a bad. Understand?
yes, sir.
Yeah. If f of x is linear, then you should expect only this one. If you are getting this one, that means there is no more linear. Yeah, think questions. Asking like this is a kind of like you are clearing the lot of clutter, which may be on doubtful things. Just discuss. Question ourselves. Question me.
So in neural networks, there is a one function's activation which control the sir value, sir. Like if we just affine function is
Yeah,
also linear function, sir. And then
yeah.
if affine functions like not converge, then our activation function to push that value in convergence. Like if we use sigmoid
Mm,
function, then sigmoid always 0 to 1. Then after
mm,
that we put some extra constant in that sigmoid value,
mm, mm,
activations value, then we
mm,
will get our final output. This there is a controlling also key if we approximate any function, and if our function approximation is not converged, then we in neural network we can use our best activation function to control the convergence. But in Taylor series, I think there is not any kind of controlling powers.
mm.
Or
So Taylor series. So that means like we cannot do this approximation in the Taylor series for every function.
so we can do, sir, but for more better way if we use neural network,
So more better
in my
way or
opinion.
that we cannot okay so Taylor theorem, I think you know it. Taylor theorem. Taylor theorem says something if you have the t of x is a you have a target Taylor series minus f of x, the error is always bound by something called modulus of f of n plus 1 of 0 by n plus 1 factor. Something you read this theorem
Yes, sir. Yes, sir.
somewhere around in your first semester or second semester somewhere. That means like this is deciding your epsilon so that you can get the approximation as much as close as this one. In Taylor theorem, actually, you have something explicitly written this epsilon. You can think of it. What epsilon you want, what higher order you can go ahead. But in neural network, we don't have that bound to explicitly define that how our target function, let's say our f of x, is close to our target function g of x. Of course, it is saying very strongly, neural networks is also saying very strongly that the dense class, that is from the density point of view, and here it is a point of view tells their approximation. I am putting a lot of information which you know already, and I am questioning in the discussion way. Now we are trying to look at the scenarios of these things. So, like if Taylor series is doing much better, as you know it from the mathematics, why can't Taylor series, another further discussion or further way of saying, why can't Taylor series or um, why can't I could say it this way? Mm, and the way of asking may be quite different. Why can't artificial intelligence or modern these prediction models not on Taylor based models? Why on neural based models rather than? What's wrong with the Taylor? Why can't learning algorithms or Taylor based learning algorithms? Are there any Taylor based learning algorithms? Can you define one such? At least for the sake of neural network, we have a data and from some enough data from R2R, R2 to R, whatever, and given to you and ask you to compute these computations, then that means that you have generalized that function from the data. That is means that you have learned it from the Taylor series. So can I say, so this is this is also a learning algorithm which is based on Taylor series.
There is one more, I think, disadvantage of Taylor, sir. Like Taylor approximation is not applicable for not differentiable functions, sir. Like
Of course, we
mod
are
x
also
y
not.
equal
We are
to.
yeah, we are also not thinking too much on that. Like let's say some smooth functions don't have any such bumps and all. We are discarding all those. Like let's say continuous means n time differentiable functions here. So that is why derivatives are comes into the play. Think of it like you experiment in a way. Open our don't limit our thoughts, don't limit our thought process. You take Desmos or Python or whatever, look at it like you
Sir,
yeah.
sir, in Tyler we are approximating around a point, but in neural networks we can approximate in a domain.
Okay. Now somewhat okay. I will come to that point. Like what you saying, let me write it up. Like Um, okay. Um, Let me draw your idea. So let's say this is a system. Um, okay, let me choose some function. Sin x cos x. Okay, let me choose e for x in between. Something like e for x. So when you try to approximate e for x, that means let's say Taylor series around zero. That's what around a point x equal to zero. You are doing something like f of x equal to the summation I equal to 1 to infinity ai x power I by I factorial, which you are doing it. Now, that means what Taylor series, what actually you are seeing is kind of is a around point x, around a point x, right? Point x equal to zero. That's what you are doing it. What does it mean? Like is neighborhood. That's what um, you are saying. Like x equal to from a neighborhood. This is a domain. This is our domain of interest. So this domain, how big it is, how small it is, how big or how small you can approximate in this region, or in this region, or what region of interest is the choice of your approximation, right? And so this, or what is the control? What is the control, like infinity to infinity? Can I choose or not? That's the question now. So if you f of x equal to this one, a is the coefficients which you approximate, how how close you can generalize, how what interval or what domain you are looking at it. So that depends upon how much approximation you are doing it, in what length you are doing it. That is what Taylor length you can say, like at what position you are cutting it off. Okay, instead, like if you take up this one, let's say e for x, for example. E for x is a very simplest Taylor series. That's what I written this. What is the e for x Taylor series expansion? Like 1 plus e for 0, 1 plus x square by 2 factorial. Simply this one, right? All derivatives are just 1 at 0, right? X for 4 by 4 factorial plus and so on. Now, this is our e for x expansion. You know it already. Now, if I want e power something like mm, 0.5. So if I substitute e for 0.5 in 1 plus 0.5, or 1 plus 0.5 plus 0.5 square by 2 factorial equal to 1 plus 0.5 plus 0.5 cube by 3 sorry, 5 square by 2 factorial plus 0.5 cube by 3 factorial. At what point I can go so that I will get a exact e for 0.5 value? What it is defining it. So as long as you go ahead, the approximation, as long terms you go, that means you are going, and you are enlarging this capacity. The, your enlarging capacity comes based on how many terms you are keeping it. But maybe this one is very bad approximation. This one is somewhat closer. This one is some much closer. Maybe further, if you take up a few more times, that may be much closer. That means like if you truncate up to here, that is the x equal to 0. It is very close. As you taking x for 4, it may be expanding. As you go 100 times, it may be close much larger length. That's what it is actually defining. So now the question is about, like, are we really approximating e power 0.5, or whatever. Like if I ask you e for 100, and you e for 100, if I ask you like 1 plus 100 only, the first two times if I take it, is that a good approximation? It definitely not. It is far away from the x equal to 100 somewhere here, and you just approximated only the first order linear approximation. That means like you have something like this one only, the line equation. So this maybe matches very close to this one, very close, that is at zero only. If you take quadratic, it may comes like the some kind of a quadratic approximation comes like this. It may be somewhat expanded domain. So this is how the Taylor series is approximating this e for x based on the number of things. The domain of interest is actually playing a role of what terms of length you are choosing it. So again, it is a domain is the domain of interest, the data which you are generating, data which you are collected, that is based on your consideration of the point which you are expanded. So if you are talking about you want to approximate e for x in the interval something like -2 to 2, then you should take care what how many terms you should take care such that the approximation, the Taylor series approximation exactly matches with this one, out of which you don't care whether it is going out this way, that doesn't matter. Definitely it goes if you are cutting it off after certain stage. So again, there is a domain of interest is here, and for that accordingly you are choosing the length of approximation. This argument is not always true, especially for the functions continuous. Only let's suppose one argument I wanted to give. You are agreeing with what I'm talking right now? The Taylor series approximation, how it is looks for e for x. You may be satisfying the results with approximation by taking it. But now if you think of very carefully, if you take f of x equal to e for x equal to this one plus x square by 2 factorial plus and so on, you think really the coefficients which you are sitting here all are what? The AIs. AIs are uh, d e for x by dx at x equal to 0, that is 1 everywhere, right? X equal to 1 everywhere. So now graphically I wanted to say something. So the same e for x, if you take up like this one, so that means like you are approximating at x equal to 0. That means ever you are doing around this one x equal to 0. And now if I change these functions, if I maintain, let's say this around x, I maintain some part up to here, it is okay, then I, this is our e for x, let's say. And now I change the some new function like this, I change some new function like this, but around x equal to 0, and this new function, let's say g of x, is another new function. This is e for x is your original function. Now if you look at this f of x, it is literally using the coefficients from this one only, near at x equal to 0. For my g of x is also it is satisfying, right? For my g of x is also the derivatives all like d g of x by d of x at x equal to 0. All my derivatives are also 1. Am I correct or not? Means because of I maintained a local neighborhood is equal to e for x at x equal to 0, some around some epsilon neighborhood I may that is equal, and rest everywhere it is different. So how can I justify the g of x, but now nowhere g of a for x. My one is g of x. So can I keep this as also a g of x? No, right? This is literally no. You understand what am I asking, Dhanush? So yeah, yeah. Please involve. This is a really interesting things which you know all these things, but need to explore deeper insights. You know e for x. I given a g of x where e for x is matching with x around x equal to 0. Can I say my g of x is not satisfying Taylor series? If you do Taylor series expansion around g of x, you will get the same as e for x or not.
Yes, sir, it will satisfy.
Satisfies. But g of x is something different.
Yes, sir.
So how do you give justification or judgment that like the Taylor is completely rude or waste or what? Why this
It is
anomaly?
good only for around the local points, sir. If we are approximating only at local points.
Yeah, this only this one. That is good. Like if it is that one, but when you come out of this bond, then it doesn't know it actually. What is going outside of it? But the crazy thing is comes here in the picture like e for x equal to the expansion is true for all real number, or especially for e for x. It is true for all real numbers. It is not a local. Then how this expansion says that for all x belongs to R it is true. You studied this expansion or formulae or whatever without looking at these scenarios. This whatever I raise this scenario. But now if I ask questions like this, then whether this formula is wrong or what, like how do you convince? In when you study first time, maybe in your plus two or somewhere, for all x belongs to is true. There is no such mention like it is a local. For when I counter this one with something g of x, with that LR with where it is only matching with the local with x equal to 0, then something is there. What is missing? Okay, this is what where the term comes. The term is called analytic. Have you heard this word analytic? Analytic functions, the real analytic functions, or analytic functions, I can say. Do you know this one or not? Analytic functions. Hello, have you heard this analytic functions? I hope you have already come across somehow around analytic functions.
Yes, sir. I think last time in complex analysis.
Yeah, complex, of course. That's thing for analytic. So it works for real too. So now the argument, whatever I am giving, this one, and this e for x and sin x, cos x, all polynomials, all are analytic functions. But my crazy functions like g of x, like let's say g of x equal to some piecewise continuous functions like e power minus 1 by x or x square with 0, and let's say x greater than 0 or x less than 0, there's something like they behave something like, they comes like always 0, this one, this somewhere go like this. So the behavior of this one here would be different. Even here for these kind of functions, even it is a continuous function, but Taylor series doesn't hold here. So you cannot get an expression for Taylor series for these kind of functions to satisfy for all x belongs to R. So the functions, I can say very clearly two things like smooth versus analytic. When I can close with something like smooth versus analytic are quite different. All smooth functions are not analytic. Smooth doesn't imply analytic. What are analytic? Analytic are the Taylor expansions. The Taylor expansions are matching with the original function for everywhere. For all x belongs to R, not a local. Understand? Taylor expansions are satisfying f of x with t of x for all x belongs to real number. Then we say those are all analytic functions. They are not local behavior. But some smooth functions, if you choose like this one, like my g of x, like whatever I mentioned, like this one, the somewhere it is mentioned the Taylor expansion around a point, and but it is something different. It is g of x is not matching with the Taylor expansion at x equal to 0. That is matching with only for x, and then my g of x is not a analytic function. So the Taylor expansions, whatever you remember, sin x Taylor expansion, you know it, cos x expansion, you know it. Why those are all comes as expansions? Because they are true for all x's. So you don't need to worry about those series are true. That is why you don't get the expansions for some kind of crazy expansions. Like if you take any kind of function you choose, like this one, my g of x, you don't have a series expansion for satisfies for all x belongs to R, infinite series. So those functions which have the infinite series Taylor expansion, with which is true for f of x for all x belongs to R, it's not a local. Then those are all analytic functions. That is a clear distinction with analytic. The smooth functions are continuous functions, you know it, but every continuous function cannot be analytic in real. So the analytic functions I am targeting here, that is why the difference between the argument, whatever I am showing here, because of e for x is analytic and g of x is not an analytic. That is why you cannot express this as a continuous function from the local property. So analytic functions, for the case of analytic function, if you say some random analytic function g of x or h of x, some analytic function, what does it mean? That if you know somewhere it's local information, somewhere local information, that means the function is something like, the function is going like this way. I don't know what's going outside, but I know all the derivatives at this point, all the higher order derivatives like h n of x, nth derivatives, all the higher derivatives at x equal to a. Then if I know that this is analytic, if it is analytic, that means that Taylor series exists, that infinite series, then that doesn't need of any what's going there. I need this information is sufficient for me to construct the entire function. That is the AIs, the coefficients, whatever I am targeting here, that is sufficient for why I am writing x of x. That is x for I by I factorial. is equal to 1 to n. So if I know local derivatives, then that's done. My h of x is ready. So now that is why the those analytic functions are very few. That is all polynomials and e for x, sin x, cos x, and any linear combination of all these again analytic function. If suppose e for x into not only linear combination, any combination by cos x is again analytic function. So that meaning is that you can bring down to an Taylor series expansion. It holds for all x belongs to R. It's not a local anymore. That is the distinction between analytic. I think the analytic is especially for the case that one. In the complex case, is quite different. Every smooth is analytic there. If it is, and also already analytic continuity, if a function f of z is having a first derivative, that means it is having all its derivatives. The all higher order derivatives it exist, and they are all analytic functions. That is a quite different story. I'm not touching that one. So yeah, so now coming down to analytic functions, instead of very first I started with something like continuous functions. Instead of continuous functions, if I take only analytic functions, and if I get approximation of this one, and which one is good, neural network or Taylor series? So for this, you do experiment, like I will write up some random experiments, mathematical experiments. Uh, Take functions of some polynomials, let's say polynomials x square, or some any 3-degree polynomials, ax cube plus bx plus c, uh, cx plus d, some quadratic cubic polynomials, some transcendental e for x or sin x, cos x. You take all these and don't go anywhere, just stay around zero, and do experiments with Taylor, like try to expand the approximation t of x with summation ai x power I by I factorial, and get the AIs, get the AIs, and now the same f of x you take with the neural network, especially from the sigma net, from the sigma nets, like the expressions, it like mm, beta is some g of a of x. Okay, I'm not writing everything. Yeah, I equal to 1 to some k. So now here you have to approximate a lot of coefficients here, which are involved here, and here also a lot of coefficients are involved. So now come to some kind of so like take a data, not from the function, take data of a particular function. Let's say if you take f of x equal to x square, and get the data from x square. Don't take exactly x square, you take x square plus or minus epsilon, so that you keep the set x square plus or minus epsilon. The epsilon is take it up with some noise you are adding with the original data, and now use those entire data to do Taylor and to do neural, the sigma nets, to get these coefficients, Taylors in the AI coefficients and the neurals in the the neural network coefficients, whatever weights involved in it. Okay, now come to look at with original f of x with approximate with the t and f of x with the neural function n of x. I could say approximation. And now think of it like which one is coming much closer and what circumstances they are doing. It is a purely, I'm not making it too much concrete and thing and a lot of details gave it to you to experiment on your own way. It's a own your own free will to look at the Taylors and the neural networks. This is just to explore mathematics into connecting other parts of the mathematics with what we are currently doing it. That's what my convention like. Not only just if you are comfortable with the Taylor, replace Taylor with something like what is called Fourier and replace Taylor with Fourier and what's happening there. So you just play like a kid, take things, do work, and look at them, formalize them, visualize using Desmos, Python, write the codes. It is a way of learning. It is if you do these experiments, maybe experiment may be very bad experiment, bad thought. That is very good. Something you have started with, and you come to some conclusion. That means you cleared off a lot of other areas of knowing the things. Like it is to judge, to justify, to judge the mathematics and the rules, whatever. Yeah, yeah. You can ask me questions, and I'll close up. Otherwise, hello. I think very few of you are there. Rishabh, are you there?
Yes, sir.
Yeah, fine. I You understand, all of you, like what I was conveying to you to look at the things in various dimensions of thinking. So it is up to you that how you spend the time with the stuff. It's not about me how I am throwing at you.
Yes, sir.
Yeah. So because I am looking for the discussions comes once you try experiment, then you have a lot of stuff to ask me. If you don't experiment, you don't actively participate, no. Like you passively listen, passively goes away, and you experiment it. That's what my intention. Okay, then if you don't have any questions, um, we will discuss. This is a kind of off discussion, but it is a very good discussion to experiment much detailed way. So we will continue in the next class with our neural networks and the rest of the things. Okay, thank you.